For half a century, there's been this one biological question that has sparked just endless debate. And today, we're going to see how a completely different field of science might have just cracked the case wide open.
You've probably heard of it, right? Maybe you've even felt like you've experienced it, this idea that when women spend a lot of time together, their menstrual cycles start to align. But is it actually a real thing?
Well, you might be surprised to hear that even though this has been studied since the 70s, the scientific community is, deeply divided. There is absolutely no consensus on whether this phenomenon, which is called menstrual synchrony, even exists. But what if the problem isn't biological in the way we've been thinking about it? A recent paper suggests that maybe we need to look at it through the lens of strategy, almost like it's a game, to finally make sense of this whole mystery.
So here's our game plan. We'll kick things off with that 50-year-old mystery, then we'll bring in game theory. We're going to build a simple game. Then we'll add a little envy, a final twist of uncertainty, and see if we can land on a much more complex and maybe more satisfying answer.
All right, first up, let's rewind the clock and go back to where this all started, the big debate over something called the McClintock effect.
It all kicked off in 1971 with a paper by McClintock, but that initial excitement, well, it soured pretty quickly. For decades, criticism just piled up. Studies trying to replicate it failed, and experiments just kept producing this messy, contradictory data. The whole idea was kind of left in scientific limbo.
This quote really captures the mood in the scientific world. By 2013, a lot of researchers basically felt the evidence just wasn't there. That simple question of, does it happen, had no simple answer, and that's pretty much where things stood. Until now.
So let's bring in our new tool and see how it builds a totally different kind of explanation. We're going to shift gears from asking if it happens to asking why it might happen, from a strategic, evolutionary point of view. Now, the key idea here with evolutionary game theory is that the players aren't making conscious choices. Evolution itself is the one testing out strategies over millions of years and picking whatever works best. A female doesn't consciously choose when her cycle happens, but evolution might have selected for a certain timing that gives her an edge.
Okay, to build our model, we've got to simplify things. Let's say we have two players, FA, who is the male's preferred choice, and FU, who is his second choice. And look, this isn't about judgment, it's just a simple way to model mating preferences in a system.
And here are the rules of the game. The setting is a simplified group, just one male, two females. The choice, which is really driven by evolution, is for a cycle to happen in the first half of the month, let's call it T1, or the second half, T2. And the goal for each female strategy? It's simple. Maximize your reproductive opportunities, which we'll represent by time with the male.
Okay, we have our players, we have our rules. Let's build our first, most basic game. But I'm telling you, the result is going to be the exact opposite of what you might expect.
All right, let's break this down. If both females have their cycle at the same time, say T1, the male chooses his preferred partner, FA. That means FU gets zero mating opportunity, nothing. But look what happens if they choose different times. Suddenly, they both get a chance to mate. The logic here is pretty clear.
So the most rational, evolutionarily stable strategy is for the females to separate their cycles to avoid competing. Our first, simplest model doesn't just fail to explain synchrony, it actively predicts the opposite should happen, and that is the Harem Paradox.
But that first model is all cold, hard rationality. What happens when we add a powerful and very human emotion into the mix? Let's introduce the idea of envy to our game.
Okay, let's add a small envy bonus. It's represented by that little epsilon symbol there. This is just the extra psychological value the preferred female gets from winning when they both compete at the same time. It seems like such a tiny change, but it completely destabilizes the whole game.
With envy now in play, there's no longer one single best strategy. The attractive female is now tempted to sync up just to get that extra win, but the other female is still way better off separating. The game's stable outcome becomes, well, a mixed bag.
So now the model predicts that synchrony just happens randomly, 50% of the time. And this is a huge step forward. It suddenly gives us a reason why the real-world data has been so messy for decades. I mean, if the outcome is basically a coin flip, it's no wonder scientists kept getting different results. But wait, there's one final twist. We've been assuming the male's preference is totally fixed and clear, but what happens if we introduce just a little bit of uncertainty on his part? With male uncertainty and enough envy in the mix, the game completely transforms. It's not about one person winning at the other's expense anymore. It becomes what's called a stag hunt game, where the biggest possible prize can only be won if both players cooperate and coordinate what they're doing.
And this is the final amazing result. Under these specific conditions, strong envy and male uncertainty, the most rational strategy for both females is to actually synchronize their cycles. The McClintock effect, the thing our first model said was impossible, suddenly becomes the most likely evolutionary outcome.
So let's put this all together. What does this new perspective really tell us? Well, it's not about a simple yes or no.
So the key takeaway is really this. The 50-year debate was stuck because it was asking the wrong question. It isn't a simple yes or no phenomenon. Synchrony is an evolutionary strategy that only shows up under very specific social conditions. And this game theory model, with all its messiness and mixed outcomes, finally helps explain why the real-world data has been so confusing for so long.
And this leaves us with a final, pretty provocative thought. If a complex biological mystery, like this one, can be unlocked by thinking about it as a game, what else are we missing? What other parts of our lives, our biology, our societies, are actually governed by these hidden strategic games we don't even know we're playing?